This is Formal Methods Lecture 15, Recap. And we have two topics today, monotonicity and deduction, which is also known as assuming the conjuncts of the antecedent. So let's get started with monotonicity. Now last time we actually proved one of these, I think it was 4.2 monotonicity of or. And now what we want to do is see how monotonicity is used. And the point is that it is necessary, monotonicity is necessary in some proof steps. And the way it is used is slightly different from the way we have done proof steps up until now. So let's start with this example. Suppose you are doing a proof, and in the process of doing that proof, one of the lines, the last line that you have in your proof is P and S, and you want to make another step in the proof. Okay, so here is an example of a proof step that is legal and how you would use monotonicity. In this case, monotonicity of and, 4.3. Okay, so here's our one step in our proof, P and S. So we assume that there have been previous steps that are not shown here. We're just showing one step in a long sequence of steps in a proof. And so we have P and S. And now in this step we are going to use 3.76a, and I have reproduced it here in the hint. 3.76a is P implies P or Q. Now, notice that we have P in our step, right? And to use 3.76a, we know that P implies P or Q. Now, so the following step would be to replace the P with P or Q, but because P does not equivalent P or Q, because P implies P or Q, then the next step is P or Q, open paren, P or Q, close paren, and S. In other words, we have substituted for the P, we have substituted P or Q, but because P does not equal P or Q, because P implies P or Q, we have P or Q and S. But now here is the thing. We have to include this phrase in the hint, and 4.3 monotonicity of and. Now why is that? That is because because we have and S. So do you see that P is one of the conjuncts of P and S? The other conjunct is S. So monotonicity, 4.3 monotonicity of and, is what makes it legal to replace P with what it implies. So think of it this way. If P implies P or Q, then P and S implies P or Q and S. That's what monotonicity of and is telling us. All right, now here's another example. This time we're going to do monotonicity of or. Suppose you have P or and another expression, in this case open paren, S equals R, close paren. Then the following proof step is legal. So here we are, we have done a number of steps in our proof, and in the middle of our proof we have this expression, P or open paren, S equals R. Now, and here again, let's use 3.76a. Now 3.76a says that P implies P or Q, right? So we can replace the P with what it implies, right? And we can bring down the S equals R, but what are we bringing down? We are bringing down the fact that S equals R is a disjunct, not a conjunct, but a disjunct. You see the left here, let's go back. You see the left disjunct of this is P, and the right disjunct is S equals R. Okay, so 3.76a says that because P implies P or Q, we can replace the P with P or Q. So here's our P, and we can replace it with P or Q on the next line. But we also have to quote now here 4.2 monotonicity of or, because P is a disjunct and S equivalents R is a disjunct, and so we are using monotonicity of OR 4.2. Now this is kind of a different way to write a hint, because up until now it has been possible for us to write just one previously proved theorem in the hint and use it together with substitution and Leibniz, or in this case implication, together implication or mutual implication by itself. But now this hint is unique in that it requires two previously proved theorems, 3.76a and 4.2, and furthermore they cannot be separated. It is not possible to do 3.76a in one part, in one step, and then 4.2 monotonicity in another step. They are intricately bound together, and they both need to be quoted in this hint. Now, and this concept of monotonicity is always a little bit elusive and a little bit tricky to wrap your head around. Now the next few slides will show you exactly how 4.2 monotonicity is used. Let's look at monotonicity of OR, the disjunction, 4.2, monotonicity of OR. Okay, so let's start with P or R. Now this P or R, you see, is the P or R in 4.2 monotonicity of OR. Okay, and now the next step would be implies, and then you give a reason why P implies Q. And I think in the previous slides it was, what was the number? The reason was 3.76a. 3.76a is why P implies Q. Okay, so we have a reason why P implies Q. And so the step is P or R implies Q or R, which is underlined in red, and then the antecedent of monotonicity of OR is the first part of the hint, why P implies Q. And then of course the same thing happens for using monotonicity of AND in a proof step. I won't underline the colors, but we have P and R implies, and you have a reason why P implies Q, and you use monotonicity of and then P and R implies Q and R. And so this is how monotonicity is used in proof steps. Now you have to be careful that you use monotonicity only with disjunction or conjunction. Other operations, other Boolean operators are not monotonic. For example, equivales is not monotonic. We have 4.2 monotonicity of OR, we have 4.3 monotonicity of AND. But we do not have monotonicity of equivales, because equivales is not monotonic. Now what does this mean? Now look. Suppose you have P equivales R or S. Okay? And you know that P implies Q. The following proof step is not legal. You can't start with P equivales R or S. Are you with me? And say that implies, by 3.76a, the fact that P implies P or Q. It is not the case that P or Q equivales R or S. This is illegal, because equivales is not monotonic, you see. So you can use monotonicity of OR and you can use monotonicity of AND, but you cannot use monotonicity of equivales. You can't just take any variable anywhere in a Boolean expression and replace it by what it implies and expect the whole thing to imply the whole thing with that substitution. It only works for conjunction and disjunction. And here's another one. Not only is equivales not monotonic, but negation is not monotonic. So here is an example of an erroneous proof step. Suppose you have not, parentheses, P and Q. Okay? So here we have a proof step where we're starting with not, parentheses, P and Q. Now check this out, you guys. There is a theorem, namely 3.76c, that says P and Q implies P or Q. Well, you can't just take that P and Q and replace it with P or Q and expect it to imply that. This is illegal. It is not the case that the negation of P and Q implies the negation of P or Q because P and Q implies P or Q. Because negation is not monotonic. So you see, the reason we emphasize the monotonicity of and the monotonicity of or is because these properties do not apply to other Boolean operators such as equivales and negation. Okay, so this is always a little tricky. I think you might have to replay this a few times before it kind of clicks. But we don't need to use monotonicity that frequently. It only happens maybe 3 or 4 times, maybe 5 or 6, maybe half a dozen times in the course, throughout this course. But when it does happen, it's important to know what to use it properly and mathematically correctly, logically correctly. Okay. Now the next thing we are going to learn is a proof technique, and we are going to use a metatheorem. A metatheorem is a theorem about theorems. Now here's another thing about these proof techniques that we are learning in Chapter 4. Technically, it is legal to use these proof techniques only after Chapter 4. In other words, we are introducing these proof techniques in Chapter 4, right? So, on the other hand, I have tried my darndest to have a good exercise sets, good proofs of theorems that we haven't learned before, but it's just so hard to do. So I'm going to introduce the concept of what's called I'm going to call a reproof. Because they make good exercises, we will illustrate the proof techniques by reproving previous theorems. So strictly speaking, they are not legitimate proofs because we are using a proof technique that comes later after the theorems that we are proving. But they just make such good exercises that, like on an exam or on a homework assignment, if I say reprove something, well, strictly speaking, it's not illegal to prove it that way, but we're going to do it anyway, just for practice. So we just have to realize that these reproofs are technically not legitimate proofs because they are using proof techniques that come after the theorems. So a lot of these theorems in Chapter 3, I'm going to ask you to reprove them using these proof techniques. Okay, so now here is our big metatheorem proof technique. It is called deduction. And deduction is also known by the phrase assume the conjuncts of the antecedent. So both deduction and assume the conjuncts of the antecedent, both of these are the same thing. I'm kind of liking the phrase deduction instead of assuming the conjuncts of the antecedent, which I emphasized in earlier years. But anyway, that's neither here nor there. And here's how deduction works. To prove that a theorem of the form P1 and P2 implies Q, what you do, and this seems kind of strange, what you do is you assume that P1 and P2 are theorems. You assume that P1 and P2. In other words, you use them as if they are theorems. And then you prove Q using P1 and P2 as if they were theorems. And furthermore, there is an additional restriction that is described in our textbook. This restriction is that you cannot use textual substitution in P1 or P2. Okay, so now we're going to show how this works by using an example. We are going to prove that P and Q implies P equivales Q. Okay? So that's what we are going to prove, and we are going to prove it using deduction. In other words, we are going to assume the conjuncts of the antecedent. Now, do you see that in this particular example, the P1 is the little p, the P2 is the little q, and the P equivalence Q is the capital Q. All right, so you see this is of the form P1 and P2 implies Q. Right? Now here's how it's going to work. It says, and prove Q. So we don't start with the whole thing, we start with Q. Now what is Q? Q is the consequent. So in our proof, we will state that we are using deduction. Okay, so proof, colon, underline the word proof, colon, and then let's say deductions, so that the reader knows that we are using deduction. So when we use deduction, what do we start with? We start with the consequent, Q. And what is the consequent? It's P equals Q. So now, we don't get this to a previous theorem. We don't, well, actually, we do get it to a previously used theorem. We get it to true. That's because true is a previous theorem, right? Okay, so now here's what we do. Now this seems kind of strange, but here's how we're going to do it. Because we're using deduction, we're going to say equals. And now, what are the two conjuncts? The two conjuncts are little p and little q. And so here's how we write the hint. Assume conjunct p. Well, if we assume conjunct p, that means in place of p, we can make that true. So we say true equivales q. Okay, now, what about q? We can assume conjunct q as well, can we not? So we say equals, assume conjunct q, and what that does is that makes q true. Okay, but now this looks familiar. True equivales true. Isn't this one of the very first ones we learned in chapter 3? I think it was 3.5, reflexivity. So that is a previously proved theorem. True equivales true. And we could have used, I think it was 3.3, and gotten that to just be true. But at any rate, this is how it works. Now, it seems kind of like strange that this proof technique will work, but if you think about it for a minute, it's all quite logical. Now at this point, let's summarize how to prove P1 and P2 implies Q. We have actually learned 4 different ways to do this. I don't know if you realize this, but we have gone over 4 different ways to prove that P1 and P2 implies Q, and I have summarized them here in this table that we're going to look at here in a minute. And it's easy, there are slight differences with each one, and it's easy to get confused to mix these up. So I've summarized it here in a table. All right, so now let's start at let's see how we did this at the very beginning, at the very get-go of this course. Do you remember when we explained how a theorem is proved? We said that it was equivalent to a previous theorem, and some of the proofs that we do, we still use this technique. We start with the whole thing. So if we use this technique, the equivalence to a previous theorem, then you start with the entire theorem. So in this example, or in this instance, using this proof technique, we would start with the entire theorem, and it would look like this. Here's how the proof would look. We would start with P1 and P2 implies Q, and then we would do some hint and get another expression, and do some other hint and get another Boolean expression, and get some other hint, and so do some other one, and eventually we would get it to a previous theorem or true, because true is, well, I mean, true is a previous theorem for most of the theorems in our system. And when we do it this way, notice that all of the operations on the left-hand column are equals. Okay, so this is how you would prove P1 and P2 implies Q, by getting it to equivalent a previous theorem or true. And in that case, in that instance, all of the operations on the left on that left column are equals. Then a few lectures ago, we said, okay, now in the same way that you can start with one side of an equivalence and get it to equivalent another side, you can also start with the left-hand side of the implication, the antecedent, and get it to imply the consequent. Now when you do the proof this way, what you would start with is you would start with the antecedent. Okay, so you would start with the antecedent, and in this way to prove P1 and P2 implies Q, you would start with P1 and P2, and then you would use a hint and get it to equal something else, and then along the way you might use an implies with a hint and get it to equal to another expression, and then you might use an equals with a hint and get it to something an equals, and then later on in the proof you might have another implies with a hint, and eventually you don't get it to a previous theorem, you get it to Q, you get it to the consequent. All right. Now in this style of proof, each operation on the left-hand margin, on the left-hand side, each in the first column of the proof, has to be either an equals or an implies. Remember we said that we could not mix them up. You always have to have implies here, equals or implies, because equals and implies are together transitive. Okay. Then what we said is you could do this the other way around. So you could start with the consequent and show that the consequent follows from the antecedent. Now when the consequent follows from the antecedent, what you do is you start with the consequent. And now what is the structure of your proof? What does it look like? It looks like this. You start with the consequent, so you start with Q, and then you use some hint and you get it to equal some other expression. And then you might use the follows from operation and get that to follow from something else. And then you might use follows from again and get that to follow from something else. And then you might have that equal something and by some hint. And then wind up with P1 and P2. Now, if you do it in this direction, then all the operations in the left column are either equals or follows from. Are you with me? Now what's kind of slightly can be confusing here is that when you use deduction, and another word for deduction is assuming the conjuncts of the antecedent, what do you start with? You start with the consequent. All right, so we're going to start with Q, but notice how this proof works. This proof technique, this meta theorem that allows us to do this. It looks like this. You start with the consequent Q, but you do not use implies or follows from. Everything has to be equals. But then what you do is you, along the road from the first line to the last line of the proof, in the hint, you can use P1 as if it were a theorem. You see? So here in this example, or in this kind of format, in this general format that I've shown here, the first hint says assume conjunct P1, and you would get some expression, and that might equal something, and you get another expression. And then somewhere along the line, you could assume conjunct P2. So wherever you have a P2, you just make that true. And eventually you wind up with the previous theorem or true. But now look, this looks similar to the previous proof technique where you prove by showing that the consequence follows from the antecedent, but it's because both of them start with Q. But notice that it's way different in two respects. First of all, every operation on the left-hand column must be equals when we use deduction, and furthermore, you don't get it to be P1 and P2. You use P1 and you use P2 as if they were theorems. Now, I think when you look at it this way, do you see why it makes sense to use deduction? Because if you assume that because what you're trying to show is that P1 and P2 implies Q. So if you use P1 as if it were a theorem, well, if it were true, if it is true, then Q will be true. You see? So I explained this in the lecture that this is a difficult one to show logically precisely why why deduction works, but it makes sense. It takes a while to to wrap your head around it. But it's work. Everything. This is all legal. I wouldn't have you do anything that's illegal. Okay. Anyway, good deal. That's it. See you next time.